All right, this is Aerospace Engineering Debrief on Truss Reaction Forces 3. Homework assignment assigned, maybe back in November or so. For each truss, calculate the reaction forces and then go inside the truss structure and calculate the tension and compression for each member. All right, the first one was, I have this truss structure that you see here visually, and I have a load applied of 100 units. Let's declare that the units for the forces are in newtons and the units for the distances are in meters. So on the outside, we have this 100 Newton force applied vertically downwards. And the sum of all the forces in the vertical direction have to add up to 0. So we know in the end, we're going to have two vertical forces, and their total has to add up to 100 newtons up. But wait, there's more. There's also a moment being created. So if I choose, for example, my favorite pivot point on the left and treat that as my axis of rotation, then this 100 Newton force is trying to make the truss structure rotate clockwise. This is a negative moment. And to counter it, I have to apply a counterclockwise moment. The only place where I can do that is on what I'm going to call point B over here. So point A is the left side, point B is the right side, and the top of the structure, I'll label that one as point C. So my first task really is to make the moments about point A add up to 0. And by the way, I've never bothered doing this before, but I could have just as easily put my axis of rotation at point B and said, oh, so the 100 newtons at the top at point C here is making a counterclockwise moment about point B, and the only way I can cancel that is to have a clockwise moment through point A. And I can solve for what is the vertical upward force at point A using my axis of rotation over here on the right. I'm allowed to do that. There is a third way you could do this where you put the axis of rotation here, but that's more math than we need to bother doing. I'll just go back to doing it my favorite way. I'll put the axis of rotation to point A and say what's going on here. I have 100 newtons. Now, I could use Pythagorean's theorem and say the distance from A to B is 3 radical 2, because this is a 3 radical 2 right triangle. This is R, the distance from A to C. Taking that direction to be the 0-degree direction. Oh, apparently it's not quite exactly 3, 3. 1, 2, 3, 1, 2, 3, 4. I'm sorry. So this is a 3, 4, 5 right triangle. It's 5 meters exactly to go from point A to point C. And the angle is listed here as 53.130 degrees. But the angle theta is measured from the direction of R, which is this direction from A towards C as 0-degree line, to the direction of F, which is this change here for my pen. So from up here to down there is a change of 53.130 degrees plus an additional 90 degrees, all in the negative direction, the clockwise direction. So if I want to use the moment formula R cross F, I would use the value of R is equal to 5 meters, F is equal to 100 newtons, and the angle between them would be 143.130 degrees, the sum of 53.130 plus another 90. And when I do that on my calculator, I'll get the moment about point A. But I like doing things where I slide the force along its line of action until I make it a 90-degree angle. So this becomes 1, 2, 3 meters, 100 for the value of R, 100 newtons for the force, and negative 90 degrees for the angle between R, which is now along the positive x-axis, and F, which is vertically downwards. This is negative 90 degrees. The sine of negative 90 degrees is negative 1. So I can do this one in my head and say the moment must be negative 300 Newton meters. That is the moment about point A caused by load 100 newtons at this location up here. And I'll write that down in some scribbly little place and say the moment of this load is equal to negative 300 Newton meters. And we're going to pretend that these are all the 3 sig figs here, these measurements. To cancel that, there has to be an upward moment through B of positive 300 Newton meters. Well, R is 1, 2, 3, 4, 5 meters. F is going to be vertically upwards, and the angle between R along the positive x-axis and F, which is vertically upwards, is going to be positive 90 degrees. The sine of 90 degrees is 1. So I'm going to have 300 Newton meters is equal to 5 times the reaction force at B. 300 divided by 5 is 60. So I have established that the reaction force at B has a magnitude of 60 newtons upwards. That is at B in the y direction, and it's positive, it's upwards. 60 newtons upwards is the reaction force at B, so that its moment cancels the moment caused by the load. Now I'll go back to the first comment I made that says the sum of all the forces in the vertical direction have to add up to 0. So if I have 100 newtons down and 60 newtons up, I need another 40 newtons going up. 100 minus 60 is 40. So going up here must be the reaction force at A in the y direction is positive 40 newtons. And yes, there are situations where the reaction force is actually down instead of up. In this situation, the sum of the forces in the vertical direction now add up to 0. The moments about the pivot point at A add up to 0. And by the way, they would also add up to 0 if you bother doing it here. Let's see. 100 times 2 is 200. 200 divided by 5 is 40. So once again, we could calculate the reaction force at A first by choosing to put our pivot point, our axis of rotation, at point B instead. It works. The sum of all the forces in the horizontal direction have to add up to 0. You can't have a vertical force acting at point B, it would just roll. There is no horizontal load being applied anywhere in this truss structure, so there is no horizontal reaction force being applied at point A. We're done. We've just calculated the reaction force at A is 40 newtons vertically up, at B it's 60 newtons vertically up, and that's all there is. Only after we have correctly calculated the reaction forces acting on this truss structure can we now go inside this truss structure to calculate the tension or compression for each member. Let's get on with doing it. My favorite is still to start over here on the right-hand side. It's just my habit. On the right-hand side, I have a horizontal pull or push from A to B that can do nothing to cancel the upward force at B, the reaction force at B, the ground pushing upward with 60 newtons. The only thing that can cancel that is member BC, which must be pushing downward with 60 newtons of force. But it can't push vertically because it's along a diagonal. So I can only say that the vertical component of member BC must be 60 newtons. And that it is a right triangle that is similar in its components. So if it's 2 meters translation horizontally and 1, 2, 3, 4 meters translation vertically, then in this right triangle here, the ratio of vertical to horizontal is 2 to 1. And therefore, the ratio of the vertical to horizontal force is also 2 to 1. So if this thing is pushing down with a vertical component of 60 newtons, then it must be pushing to the right with a horizontal component, half of that, or 30 newtons. So member BC is pushing member B to the right with a force of 30 newtons. The only way to cancel that is if member AB pulls member vertex B to the left with a force of 30 newtons. So this member here is under tension. It's pulling in on both sides. It's pulling A and B together. So it's being stretched by the other two members, trying to stretch it apart. Member AB is trying to pull it back together. And the magnitude of this tension must be 30 newtons of tension. Okay, so really, I'm done with member AB. I can calculate the hypotenuse of BC by saying, look, its vertical component is 60 newtons in magnitude. The horizontal component is 30 newtons in magnitude, and therefore the hypotenuse is the square root of 60 squared plus 30 squared. Putting that into my calculator, it says the square root of 60 squared plus 30 squared is 67.1 newtons, I'll call it. It says 67.08203932. Now, this is pushing apart B and C. So it's squeezing the two of them apart. So it's in compression as it pushes these things apart. Now, these arrowheads ended up being too confusing in general, but this says this member is pushing them apart. These arrowheads here mean it's pulling it together. If I were to try to add arrowheads, which are admittedly confusing. So tension, 30 newtons, compression, 67 newtons. I'm done with 2 of the 3 members of this truss structure. I could do this guy on top, or I could go do point A. Either way, I can finish this off figuring out what's going on with member AC. I'll do this up at the top. What's going on here, if I do the free body diagram, is that I have 100 newtons load pushing down on point C. I remind you that member BC is pushing B down with a vertical component of 60 newtons. And so by Newton's third law, for every action force, there's an equal opposite reaction force, or forces occur in pairs. If this end of BC is pushing down with 60 newtons, then the other end of BC is pushing up with 60 newtons. So member BC is pushing up with a magnitude of 60 newtons. That's what it's doing. Now, vertically, all the forces have to add up to 0. So if I'm pushing down with a 100 Newton load, and BC is pushing up with a vertical component of 60 newtons, then member AC must be pushing up with a magnitude of 40 newtons. 60 up from BC, added to 40 up from AC, will cancel the 100 newtons down caused by the load acting at point C. So I've just established what the vertical component is of member AC. If you like, I can also point out the fact that, look, down here, BC was pushing to the right on point B with 30 newtons. So the other end of BC is pushing to the left with 30 newtons. And to cancel that, member AC must be pushing to the right with 30 newtons. That wasn't really necessary to bother doing that calculation. It's because we can already figure out what the hypotenuse is going to be. But I thought I would just illustrate that, you could do that as well. How do I know that I don't need this? Because the ratio of vertical to horizontal to hypotenuse is a 1, 2, 3 to 1, 2, 3, 4 to 1, 2, 3, 4, 5 right triangle. 3 squared plus 4 squared is equal to 5 squared. So if this guy is pushing up with 4, then his horizontal component must be 3/4 of 40. I said 4, I should have said 40. And 3/4 of 40 is indeed 30. So this hypotenuse has a magnitude of 30 squared plus 40 squared is equal to 50 squared. 50 newtons is the magnitude of member AC. And since it's pushing things apart, it is under compression. And if you want to try adding arrows, these arrows are showing member AC is pushing A down and to the left. It's pushing C up and to the right. We're done. But just to make you happy, if you like, you can sort of focus in on point A and verify what's going on. So on point A, member AB is pulling A to the right with a force of 30 newtons. The ground is pushing up through point A with a magnitude of 40 newtons. Sure enough, member AC is pushing A down with a magnitude of 40 newtons, canceling the reaction force of the ground pushing up on point A. And sure enough, member AC is pushing A to the left with 30 newtons, canceling the 30 newtons of tension of member AB pulling the vertex to the right. Ta-da! I'm done with the first truss structure on truss reaction forces 3. Now, there was a second truss. Let's see if we can do this one maybe slightly faster. Here was problem 2. And I'm going to go a little faster now. You could always replay this. First, I must correctly calculate the reaction forces. It's nice that the angles were listed, but unnecessary because this is done to scale on graph paper. So I'm going to take the 100 Newton force, the load, I should say, that is 2 meters above this vertex, and I'm going to call this A, B, C again. I'm going to slide it along its line of force backwards until it's directly above point A and say, what have I got? R is now 2 meters, F is 100 newtons, and the angle from R to F is negative 90 degrees. The sine of negative 90 degrees is negative 1. So the moment about point A, my chosen axis of rotation, is negative 200 Newton meters. That is trying to make the truss structure, I'll use the tip of the pen as the axis of rotation. That is trying to make the truss structure, and I can't really do this because I'm left-handed, rotate clockwise. To cancel that, the reaction force at B must be applying a positive moment, trying to make it rotate counterclockwise. The distance from A to B is 1, 2, 3, 4, 5, 6, 7, 8 meters. And therefore, the product of R and the reaction force at B has to be equal to positive 200 Newton meters of moment. Well, 200 divided by 8, getting too old to do this in my head, is 25 newtons. So the reaction force at B in the y direction is positive 25 newtons. The sum of all the forces in the vertical direction have to add up to 0. And I only have one vertical force. That is the ground pushing up through roller B. There's no load that has a vertical component. So at vertex A, I must be pulling down with a reaction force of negative 25 newtons. And you have to clearly indicate that the reaction force is down, not up, going to point A. Lastly, if there's 100 newtons of applied load acting to the right to point C, then there must be 100 newtons of reaction force going to the left at point A. So at point A in the x direction, the reaction force is negative 100 newtons. I have now satisfied the calculations for the reaction forces on this second truss. At point A, there's 25 newtons down vertically, 100 newtons to the left horizontally. At B, there's 25 newtons up vertically. I'm done with that. Only after I have correctly calculated all the reaction forces acting on this truss from the outside can I now go inside the truss structure and calculate the tensions and compressions for each of the members. My favorite habit is still to start at point B. So what's going on here? I have 25 newtons pushing up through point B. Member AB can't do anything to cancel that because forces in one direction are independent of forces in a perpendicular direction. So member AB can only pull or push horizontally, and that has 0 effect on the vertical 25 newtons acting through point B. The only way to cancel the 25 newtons pushing up to point B is the vertical component of member BC that must be pushing down and to the right to point B. Member BC is therefore under compression. And if you can't calculate the magnitude, at least try to indicate whether or not you believe the members are under tension or compression. That might count for extra credit. I mean, not extra credit, I mean partial credit. Whew, what was I thinking? So I'll go ahead and put the arrows in already and say, yeah, BC is pushing B and C apart from each other. The vertical component of BC must be 25 newtons. And that's equal to a ratio of 2 squares to 7 squares. 1, 2, 3, 4, 5, 6, 7. So a ratio of 2 to 7 is a ratio of 25 to whatever 7 times 25 divided by 2 is. I guess that would be 3.5 times 25. Sure, let's do that. 25 times 7 divided by 2, enter, is 87.5 newtons. So BC is pushing B to the right horizontally with a horizontal component of 87.5 newtons. That is 7 halves times 25 newtons. Guess who gets to stop that? Why, none other than AB. So AB must be under tension because it's pulling B to the left, it's pulling A to the right. It's pulling these 2 points towards each other. And that tension must cancel the 87.5 newtons that BC is pushing B to the right. So the tension must be 87.5 newtons of tension. And finally, for member BC, since I want to actually list the magnitude of the compression here, I would use Pythagorean's theorem and say, oh, 25 newtons vertically squared plus 87.5 newtons horizontally squared. According to my calculator, if the batteries are working okay, it says 91.001373662, which I'll declare to be 91.0 newtons of compressional force acting on member BC. Great. Well, I think you know my habit. My habit is to then tackle point C, the vertex. But if you like, I could have tackled point A next. Maybe for variety, I'll go ahead and do A next. Okay, so what's going on at A? The sum of all the forces in the vertical direction have to add up to 0. The sum of all the forces in the horizontal direction have to add up to 0. Right now, I have 100 newtons of reaction force pulling A to the left. I have 87.5 newtons of tension from member AB pulling A to the right. So if I were to take the difference between 100 and 87.5, that means member AC must be pulling A to the right with a magnitude of 12.5 newtons. That number alone is enough for me to calculate the hypotenuse of AC. I could just look at this geometry and say, look, the ratio of horizontal to vertical distance is 1 to 2. These are similar triangles to the forces because the forces act along the members. So the force is on the force components are also in a ratio of 1 horizontally to 2 vertically. So if I just calculated that the horizontal component of AC is 12.5 newtons, then the vertical component of AC must be 2 times 12.5 newtons. Guess what I get? I get 25 newtons. 12.5 times 2 is 25. So C is pulling A to the right with 12.5 newtons and pulling A up with 25 newtons. Therefore, it's under tension. It's pulling A up and to the right. And if I want to calculate how much, why, I activate my calculator and I ask it, calculator, what is the square root of 12.5 squared, the horizontal component, plus 25 squared, the vertical component? And it goes beep, 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 and says the answer is 27.95084.972. And I say, well, let's talk about sig figs. So 27.95 actually rounds up to 28.0 newtons will be the hypotenuse to 3 sig figs of member AC. I'm done already. If you like, as a check, you could then go and verify that the sum of all the forces acting at point C must add up to 0. G, let's see. Or C, let's see. B, the load is pushing point C to the right with a magnitude of 100 newtons. BC is pushing C to the left, if you remember, with a magnitude of 87.5 newtons. AC is pulling C to the left with 12.5 newtons. 12.5 newtons to the left from AC plus 87.5 newtons to the left from BC cancels the 100 Newton load to the right pushing on point C. So horizontally, it all adds up, literally. What else? Well, AC is pulling point C down vertically with a force of 25 newtons. Well, guess what? BC is pushing point C up with a force of 25 newtons. So the pull of 25 newtons from AC down is canceled by the push of 25 newtons from BC up of 25 newtons. Ta-da! This truss structure was solved already a couple minutes ago. This concludes my debrief on truss reaction forces 3 homework.